In the ocean, distance is your only real obstacle. In space, the barriers are so fundamental, so woven into the fabric of reality itself, that they might be insurmountable. We've sent probes beyond Pluto, captured images of galaxies billions of light-years away, and walked on the moon. Yet despite all our technological prowess, we remain trapped within our tiny corner of the cosmos, the solar system. Today we're confronting the hard truths about why leaving this cosmic neighborhood might be impossible, not just difficult, but genuinely, physically impossible, given the laws of the universe. And here's something I've been pondering. If you could leave the solar system knowing you'd never return, would you still go? What would you want to see or discover out there? Share your thoughts in the comments below. I will pin the most creative answer. Now let's begin. The solar system is our cosmic home, a region of space dominated by our sun's gravitational influence, extending roughly 100,000 astronomical units from our star. For perspective, 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. The solar system includes 8 major planets, countless asteroids, comets, and the Kuiper belt extending beyond Neptune. But even its outer edge, the Oort cloud, is just the beginning of the vast emptiness between us and the nearest stars. To understand why we can't leave, we first need to grasp the scale we're dealing with. The nearest star system to our Sun is Alpha Centauri, a triple star system about 4.37 light-years away. A light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. That means Alpha Centauri is about 41 trillion kilometers from Earth. If you drove at highway speed, let's say 100 kilometers per hour, non-stop, it would take you about 47 million years to get there. Our fastest spacecraft to date is the Parker Solar Probe, which uses gravity assists from the Sun to reach speeds of about 192 kilometers per second at its closest approach. Even at this incredible velocity, roughly 0.064% the speed of light, it would still take approximately 6,700 years to reach Alpha Centauri if it were headed in that direction, which it's not. The Voyager 1 probe, launched in 1977 and now in interstellar space, is traveling at about 17 kilometers per second. At that speed, it would take over 73,000 years to cover the distance to Alpha Centauri. These timescales aren't just impractical, they're generational beyond comprehension. If we sent a crew on the fastest spacecraft we could currently build, everyone who launched would be dead before the ship traveled even a fraction of the distance. Their children would be dead, their grandchildren would be dead. Hundreds of generations would live and die aboard that vessel before it reached even the nearest neighboring star system. But the problem isn't just distance and current technology. It's far more fundamental. The first major barrier is the speed of light itself, the cosmic speed limit that, according to Einstein's special relativity, nothing with mass can reach, let alone exceed. Light moves at approximately 299,792.458 kilometers per second in a vacuum. This isn't just really fast, it's the maximum speed at which any information or matter can travel through space. Einstein's equations show that as objects with mass approach the speed of light, several impossible things happen. First, their mass effectively increases. The faster you go, the more massive you become from the perspective of external observers, which means you need more and more energy to accelerate further. Second, time dilation becomes extreme. Time slows down for the traveler relative to stationary observers. Third, length contraction occurs. Distances in the direction of travel appear to shrink from the traveler's perspective. Most critically, the energy required to accelerate to light speed approaches infinity. You can't reach it because you'd need infinite energy, which is impossible. This isn't a limitation of our engineering, it's a fundamental property of space-time. Even if we could somehow harness the energy output of our entire sun, we couldn't accelerate a ship with humans aboard to the speed of light. Particle accelerators like the Large Hadron Collider can push tiny particles to 99.999991% of light speed, but only for individual protons weighing about 1.67 times 10 to the negative 27 kilograms. Scaling this up to accelerate even a small spacecraft, let's say 1,000 kilograms, to a meaningful fraction of light speed would require energy resources beyond anything our civilization currently possesses or could plausibly develop in the foreseeable future. Let's do some math to illustrate the energy problem. The kinetic energy of an object is calculated using the relativistic equation, which becomes critical at high velocities. To accelerate just 1 kilogram of mass to 10% of light speed would require approximately 4.5 times 10 to the 14th joules of energy. That's roughly the energy released by 10 atomic bombs. Now scale that up to a spacecraft with crew, life support, fuel, and cargo conservatively, let's say 1 million kilograms. You'd need 4.5 times 10 to the 20th joules, equivalent to the entire energy consumption of human civilization for several months, just to reach 10% of light speed, and that's only to accelerate. You'd need the same amount again to decelerate at your destination. Even reaching 1% of light speed, which would still take over 400 years to reach Alpha Centauri, presents staggering energy requirements. The most energy-dense fuel we know of is matter-antimatter annihilation, which converts mass directly to energy with 100% efficiency, according to Einstein's famous equation E equals mc squared. But producing and storing antimatter safely is currently beyond our capabilities. We produce only nanograms of antimatter per year at facilities like CERN, and it costs roughly tens of billions of dollars per gram. A realistic interstellar mission would need tons of antimatter fuel. Speaking of the incredible scales we're dealing with, if you want to truly grasp just how vast our solar system is, which is tiny compared to interstellar distances, check out my video called How Big is the Solar System?, where we explore the mind-bending emptiness right here in our cosmic backyard. The link is in the description below. Understanding the scale of our solar system makes the challenge of crossing interstellar space even more humbling. Beyond the energy problem, we face the issue of time. Even if we could somehow reach 10% of light speed, interstellar journeys would take decades at minimum. The nearest potentially habitable exoplanet we've discovered, Proxima Centauri b, orbits the nearest star in the Alpha Centauri system. At 10% of light speed, the journey would take about 43 years. That's within a human lifetime, but barely. Anyone who launched young would arrive old, assuming they survived the journey. But here's where things get darker, the radiation problem. Space isn't empty. It's filled with the interstellar medium, a thin soup of atoms, molecules, and dust, averaging about 1 atom per cubic centimeter. At low speeds, this poses no threat. But at relativistic velocities, significant fractions of light speed, even individual hydrogen atoms become deadly projectiles. A hydrogen atom striking your spacecraft at 10% of light speed impacts with the kinetic energy of a high-velocity bullet. At higher fractions of light speed, individual atoms hit with energies equivalent to small explosives. The Voyager probes, traveling at about 0.0057% of light speed, don't face this problem. But a ship traveling at 10% of light speed would encounter roughly 300 billion hydrogen atoms per square meter per second. Each impact would damage the spacecraft's structure. Collectively, they'd create a radiation environment similar to the inside of a nuclear reactor. You'd need shielding several meters thick just to protect against the interstellar medium, adding enormous mass that makes acceleration even more difficult. Then there's cosmic radiation, high-energy particles from supernovae, pulsars, and other violent cosmic events. In the solar system, Earth's magnetic field protects us from most cosmic rays. On the International Space Station, astronauts receive radiation doses about 150 to 200 times higher than on Earth's surface. On an interstellar voyage, far from any protective magnetic field, radiation exposure would be even higher. Extended exposure causes cancer, damages DNA, and can lead to organ failure. Without massive shielding, which adds prohibitive weight, crew members would accumulate lethal radiation doses during multi-decade journeys. Even with perfect shielding against radiation, there's the human factor. We've never tested how humans respond to decades in deep space. The longest continuous space mission was Valery Polyakov's 437 days aboard Mir in 1994 to 1995. He experienced bone density loss, muscle atrophy, and psychological stress despite being in constant communication with Earth. An interstellar journey would involve decades or centuries in a confined spacecraft with no possibility of rescue, no resupply, and communication delays measured in years as the ship travels farther from Earth. Psychology becomes critical. Antarctica research stations provide some analog. During the winter, when resupply is impossible, crew members are isolated but know they can leave when winter ends. Even with careful psychological screening, conflicts arise, depression occurs, and cognitive function can decline. Now imagine isolation not for months, but for a lifetime, knowing you'll never see Earth again, never walk under an open sky, never experience anything beyond the metal walls of your spacecraft. The psychological toll would be immense. Then there's the question of life support. The ISS receives regular resupply missions carrying food, water, oxygen, and spare parts. It relies on complex systems to recycle water and air, but these systems aren't perfect. Water recycling is about 93% efficient, meaning fresh water must periodically be supplied. An interstellar ship would need 100% closed-loop life support with zero resupply for decades or centuries. Any failure, any degradation of recycling systems would be catastrophic. We simply don't have technology that can operate without maintenance and replacement parts for such timescales. The spacecraft itself presents engineering challenges we've never faced. Everything we've built in space, satellites, space stations, probes, has a limited operational lifetime, typically measured in years or decades. Voyager 1 and 2, our longest operating spacecraft, were launched in 1977 and are still functioning 40-plus years later, but they're simple compared to what an interstellar ship would require. They don't support life, don't need complex recycling systems, and operate with minimal course corrections. An interstellar vessel would need to function flawlessly for centuries. Every system would need redundancy, every component would need to last or be replaceable with onboard resources, and every potential failure mode would need backup solutions. The complexity would be staggering. Modern spacecraft have thousands of components, any one of which can fail. The longer the mission, the higher the probability of critical failures. Over decades or centuries, the cumulative probability of catastrophic failure approaches 100%, unless you have perfect redundancy and repair capability. Manufacturing replacement parts aboard ship presents its own challenges. You'd need raw materials and the industrial capacity to create everything from electronic components to structural elements. This means carrying not just spare parts, but essentially a mobile factory capable of producing anything that might break. The mass penalty is enormous. Every kilogram you add to the ship requires more fuel to accelerate, which requires more fuel to accelerate that fuel in an exponential spiral known as the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky in the late 19th century, describes a fundamental relationship. The change in velocity a rocket can achieve depends on the exhaust velocity of its propellant and the ratio of initial mass to final mass. To achieve high velocities, you need either extremely efficient propulsion or you need to carry vastly more fuel than payload. For interstellar journeys, even the most efficient theoretical propulsion systems face this problem. Let's examine the propulsion options we've seriously considered. Chemical rockets, which power all our current space launches, are hopeless for interstellar travel. They can barely achieve escape velocity from Earth, reaching speeds of a few kilometers per second. Ion drives, used on missions like Dawn and Deep Space One, are more efficient, achieving exhaust velocities of tens of kilometers per second. But they produce tiny thrust. The Dawn spacecraft's ion engine produced only 91 millinewtons of force, less than the weight of a piece of paper on Earth. Accelerating to interstellar velocities would take decades, even without cargo. Nuclear thermal rockets, which heat propellant using a nuclear reactor, could theoretically achieve exhaust velocities of about 9 kilometers per second, better than chemical rockets but still insufficient for interstellar travel. Nuclear pulse propulsion, proposed in Project Orion in the 1950s and 60s, would work by detonating nuclear bombs behind a spacecraft and riding the shockwave. Calculations suggested it might reach several percent of light speed. But the project was abandoned due to nuclear test ban treaties, engineering challenges, and the obvious problem of launching a spacecraft laden with thousands of nuclear weapons. Fusion rockets, if we could develop them, would be more promising. Fusion reactions release far more energy per unit mass than chemical reactions. The theoretical exhaust velocity could reach thousands of kilometers per second, several percent of light speed. But we haven't achieved sustained nuclear fusion on Earth yet, despite decades of research. The ITER project in France, expected to demonstrate sustained fusion in the 2030s, might finally prove the concept, but engineering a fusion reactor compact and reliable enough for spacecraft propulsion remains speculative. Antimatter rockets represent the theoretical pinnacle of chemical propulsion. Matter-antimatter annihilation converts mass to energy with perfect efficiency. The exhaust velocity would be a significant fraction of light speed, making interstellar travel theoretically possible. But antimatter production requires enormous energy. You get out exactly the energy you put in, minus inefficiencies. Current antimatter production rates are measured in nanograms per year, and containment is extremely difficult since antimatter annihilates on contact with normal matter. We'd need to develop antimatter production, storage, and handling technologies that don't currently exist and might be fundamentally impractical. Laser sail propulsion, proposed by scientists like Philip Lubin, offers a different approach. Instead of carrying fuel, a spacecraft would deploy a large reflective sail. Ground-based or space-based lasers would push the sail, accelerating the craft. Since the energy source remains behind, you avoid the rocket equation's tyranny. The Breakthrough Starshot initiative, announced in 2016 and supported by Stephen Hawking and Yuri Milner, proposes using this method to send tiny gram-scale probes to Alpha Centauri at 20% of light speed. Breakthrough Starshot envisions a laser array with combined power of 100 gigawatts focused on a sail just meters across, accelerating a chip-sized probe to relativistic speeds in minutes. The advantages are clear: no onboard fuel, rapid acceleration, and the possibility of reaching nearby stars within decades from launch. The challenges are equally significant: building a 100 gigawatt laser array, keeping the beam focused across light years, protecting the tiny probe from interstellar dust impacts at 20% of light speed, and communicating results back to Earth with a transmitter weighing grams. More fundamentally, this approach only works for tiny probes. Scaling up to carry humans is exponentially harder. A ship weighing thousands or millions of kilograms would need a sail thousands of kilometers across and laser power in the petawatt range, far beyond foreseeable technology. And laser sails can't decelerate unless the destination has a laser array to slow you down, which obviously won't exist at an uninhabited star system. Generation ships represent another theoretical approach to the time problem. If the journey takes centuries, why not build a spacecraft large enough to support multiple generations? The original crew would live, reproduce, and die aboard the ship. Their descendants would continue the journey, eventually arriving at the destination star system centuries later. This concept has captivated science fiction for decades, but the practical challenges are overwhelming. First, the size. A generation ship would need to support a breeding population for centuries without genetic degradation from inbreeding. Population geneticists suggest a minimum of several hundred to a few thousand people to maintain genetic diversity over many generations. Each person needs living space, life support, food production, water, and waste processing. Even at minimal standards, you're looking at a habitat measured in cubic kilometers, with mass potentially reaching millions or billions of tons. Accelerating such a massive structure to any significant fraction of light speed would require energy resources orders of magnitude beyond what we've discussed. The fuel alone, even using antimatter, would vastly exceed the ship's payload mass. The engineering challenges of building a kilometers-scale rotating habitat that can withstand acceleration, maintain structural integrity for centuries, and provide everything a civilization needs are almost incomprehensible. Then there's the social problem. How do you govern a generation ship? Who makes decisions affecting people born aboard who never consented to the journey? What happens when conflicts arise and there's no escape, no frontier to expand into, no possibility of migration? Psychological studies of isolated communities, submarines, Antarctic stations, biosphere experiments consistently show that even carefully selected groups develop tensions over time. Scaling this to centuries and thousands of people in a confined environment seems a recipe for social collapse. The biosphere. Two experiment in the 1990s provides a sobering example. 8 people spent 2 years in a sealed 3-acre environment in Arizona, attempting to create a self-sustaining ecosystem. The project encountered numerous problems. Oxygen levels dropped, requiring external supplementation. Most vertebrate species went extinct. Conflicts arose among the crew. If we can't maintain a closed ecosystem for 8 people over 2 years on Earth with unlimited backup support, how could we sustain thousands in space for centuries? Children born on a generation ship would face unique challenges. They'd grow up knowing they were living and dying in service of a mission they didn't choose, traveling to a destination they'd never see. The psychological effects of such an existence are unknown. Would they continue the mission? Would they choose to have children, condemning another generation to the ship? What happens if a generation decides to turn back, or to stop at an intermediate point, or to simply stop reproducing and let the mission die with them? There's also the problem of maintaining knowledge and purpose over centuries. Will the 100th generation remember why they're traveling? Will they maintain the skills needed to operate and repair the ship? Will they even want to continue the mission? Cultural drift over generations could transform the ship's society in unpredictable ways. Languages might evolve, religions might change, technological understanding could be lost or preserved. You're essentially hoping that a society remains committed to a goal for longer than any human civilization has existed. Now let's discuss navigation. At interstellar distances, pointing your spacecraft accurately becomes critical. A 1-degree error at the start of the journey translates to missing your target star system by light years. Traditional navigation methods rely on known reference points, stars, pulsars, GPS satellites. But as you travel away from the solar system, your perspective changes. Stars shift position due to parallax. your Earth-based star charts become less useful. You'd need to navigate by pulsars, rapidly rotating neutron stars that emit regular pulses, which provide reliable cosmic lighthouses. But pulsar navigation requires extremely precise timing and computational resources. Course corrections present another challenge. In the solar system, spacecraft use gravity assists and thruster burns to adjust trajectory. But in interstellar space, far from any gravitational bodies, you're on your own. Carrying enough fuel for significant course corrections adds to the mass budget. Small errors compound over time. A tiny velocity error of just 1 meter per second, maintained over years of travel, results in position errors of millions of kilometers. You need continuous monitoring and correction capability for the entire journey. Communication becomes increasingly difficult as distance grows. Radio signals travel at light speed, so even to Alpha Centauri, there's a 4.37-year delay each way. Ask Mission Control a question, and the answer comes back 8.74 years later, assuming anyone at Mission Control still cares about your decades-old mission. As you travel farther, the communication delay grows, and signal strength decreases with the square of distance. Eventually, maintaining contact with Earth becomes impossible. The Voyager probes, now about 22 light-hours from Earth, roughly 165 times the Earth-Sun distance, require NASA's largest antennas to receive their signals, which arrive at less than 1/10,000,000,000th of a billionth of a watt. At interstellar distances measured in light years, the signal would be so weak that detecting it would require antennas perhaps kilometers across, and computational filtering to separate the signal from cosmic background noise. And that's just for receiving. Transmitting strong enough signals back to Earth from a moving spacecraft adds more mass and power requirements. The power supply problem becomes critical on these timescales. Solar panels are useless beyond the orbit of Jupiter. Sunlight falls off with the square of distance from the Sun. At interstellar distances, solar energy is negligible. Nuclear fission reactors could provide power for decades, but require heavy shielding and eventually run out of fuel. Radioisotope thermoelectric generators, which power the Voyager probes and Mars rovers, decay over time. The plutonium-238 they use has a half-life of about 87.7 years, meaning power output halves every 88 years or so. For a journey lasting centuries, you'd need either enormous amounts of radioactive fuel, nuclear fusion reactors that don't yet exist, or some other long-duration power source. Every kilowatt of power requires significant mass in reactors, fuel, and cooling systems. And power requirements are substantial. Life support, computers, communication, propulsion corrections, manufacturing, lighting, and heating for thousands of people over centuries. We're talking megawatts or possibly gigawatts of continuous power, sustained for longer than any human technology has operated. Target selection presents its own challenges. We've discovered thousands of exoplanets using telescopes like Kepler and TESS. Some orbit in the habitable zone where liquid water could exist, but our detection methods have limitations. We can determine basic properties, size, orbital period, approximate mass, but we can't yet characterize atmospheres or surface conditions with certainty. We're essentially picking destinations based on incomplete information. What if you travel for centuries only to find your target world is uninhabitable, too hot, too cold, toxic atmosphere, no solid surface, lethal radiation? The James Webb Space Telescope, operational since 2022, has begun analyzing exoplanet atmospheres in unprecedented detail, detecting gases that might indicate biological processes. But even JWST can only study relatively nearby, favorable cases, large planets orbiting small stars where the atmosphere's composition can be inferred from transit spectroscopy. For most potentially habitable worlds, we simply don't know enough to justify a one-way, centuries-long journey. Even if we identified a perfect target, Earth-like size, right distance from its star, signs of water and oxygen, we'd still face the question, is it already inhabited? If we detect oxygen and methane together, that suggests biological processes. But is the life microbial or complex? Would we be colonizing a living world, potentially disrupting or destroying an alien biosphere? The ethical implications are staggering. We haven't even settled the question of whether humans should colonize Mars if it harbors subsurface microbial life. Let's talk about the cosmic radiation environment in more detail, because it's truly a showstopper. In Earth orbit, the International Space Station's altitude of about 400 kilometers places it within Earth's magnetosphere, which deflects most cosmic radiation. Even so, astronauts receive radiation doses of about 50 to 200 millisieverts per year, 10 to 40 times higher than on Earth's surface. For comparison, a chest X-ray delivers about 0.1 millisieverts. On the Moon, which has no magnetic field and essentially no atmosphere, radiation levels are higher, about 380 millisieverts per year. The Apollo astronauts' brief visits didn't accumulate dangerous doses, but long-term lunar habitation would require shielded habitats. Mars has a thin atmosphere and no global magnetic field, resulting in radiation exposure similar to the Moon. This is a major challenge for Mars colonization, but at least Mars is reachable in months and could use local regolith for shielding. In deep space, radiation comes from multiple sources. The Sun produces a steady stream of solar wind, charged particles that create space weather, occasionally erupting in solar flares and coronal mass ejections that dramatically increase radiation temporarily. Galactic cosmic rays originate from supernovae and other violent events throughout the galaxy, consisting of high-energy protons and heavier nuclei. Both pose health risks, but galactic cosmic rays are particularly dangerous because they're so energetic they penetrate meters of shielding. Astronauts traveling to Mars would face several years of exposure to this environment, but interstellar travelers would face decades or centuries. No amount of shielding practical for spacecraft can reduce radiation to Earth normal levels. Water, being hydrogen-rich, makes good shielding, but you'd need several meters thickness for significant protection. At 1 ton per cubic meter, a water shield several meters thick around a habitat adds thousands or millions of tons to your spacecraft mass. The biological effects of chronic radiation exposure are well documented. Cancer risk increases, cardiovascular damage occurs, cataracts develop, and the central nervous system can be affected. Studies of atomic bomb survivors and nuclear accident victims show these effects scale with dose. Astronauts on multi-year Mars missions would face cancer risk increases of a few percent, manageable, though concerning. Interstellar crew members facing decades of exposure would almost certainly develop radiation-induced cancers and other health problems. Children born on an interstellar voyage would be exposed from conception. Radiation damages DNA, potentially causing birth defects, developmental problems, or increased cancer susceptibility. We have limited data on developing humans in high radiation environments. Thankfully, we've never had pregnant women in space for extended periods. But animal studies and terrestrial data suggest radiation exposure during development has serious consequences. An interstellar generation ship might face declining health in successive generations due to accumulated genetic damage. Micrometeoroids add another layer of danger. Space isn't perfectly empty. It's filled with tiny particles, dust grains, ice crystals, fragments from comets and asteroids, traveling at various velocities. In the solar system, meteoroid fluxes are well characterized. The ISS has shields designed to protect against impacts from objects up to about 1 centimeter, traveling at typical orbital velocities of several kilometers per second. These shields use multiple layers. An outer bumper vaporizes incoming particles, and inner layers catch the resulting debris cloud. At interstellar velocities, even tiny particles become devastating. A dust grain 1 millimeter across, weighing perhaps a microgram, hitting your spacecraft at 10% of light speed carries kinetic energy equivalent to about 400 grams of TNT exploding. These aren't rare events. The interstellar medium contains dust at densities that would cause multiple impacts per square meter over decades of flight. You'd need shielding far more robust than anything we've built, which again adds mass. Worse, at relativistic speeds, even individual atoms become problematic. A hydrogen atom hitting at 10% of light speed has kinetic energy of about 0.5 electron volts. Not much individually, but you're encountering hundreds of billions per square meter per second. Collectively, they ablate any material, creating radiation as they smash into your hull and gradually eroding the ship's structure. The front of your spacecraft faces a continual sand blasting from the interstellar medium, heating the hull and creating secondary radiation. Some proposed solutions involve magnetic shields, powerful magnetic fields projected ahead of the spacecraft to deflect charged particles. This works in principle, but requires enormous magnetic field strengths and significant power to maintain. The equipment to generate such fields would be massive. And magnetic fields only deflect charged particles. Neutral atoms and dust grains pass through unaffected. You'd still need physical shielding, which brings us back to the mass problem. Now let's examine the fundamental question. Do we even have the right to attempt interstellar colonization? Every resource devoted to building an interstellar ship is a resource not used to solve problems on Earth. Climate change, poverty, disease, education. The cost of an interstellar mission would be measured in trillions of dollars, perhaps tens or hundreds of trillions. That's money that could fund renewable energy transitions, feed hungry populations, develop medical treatments, or preserve Earth's biosphere. Some argue that becoming a spacefaring civilization is essential for long-term survival. Earth faces existential risks, asteroid impacts, supervolcano eruptions, nuclear war, climate change, pandemics. Spreading to other worlds provides insurance against extinction. But there's a counter-argument. If we can't manage to live sustainably on Earth, a planet perfectly suited to our biology, with breathable air, liquid water, moderate temperatures, and an ecosystem that supports us, what chance do we have of surviving in the unimaginably hostile environment of interstellar space or alien worlds? Perhaps our resources would be better spent on making Earth, civilization, sustainable and resilient. If we develop fusion power, clean energy, sustainable agriculture, and closed-loop recycling on Earth, we'd also be developing technologies useful for space exploration. But we'd be solving immediate problems rather than attempting to escape to hypothetical new worlds we couldn't reach anyway. The Fermi paradox becomes relevant here. If interstellar travel is possible and if technological civilizations arise commonly in the galaxy, where are the aliens? Our galaxy is roughly 13.6 billion years old. Even at modest fractions of light speed, a civilization could colonize the entire galaxy in a few million years, an eye blink in cosmic time. Yet we see no evidence of galactic empires, no megastructures, no obvious signs of intelligence beyond Earth. One possible resolution: interstellar travel is so difficult that civilizations either don't attempt it or fail when they try. Perhaps the galaxy is filled with civilizations bound to their home systems, looking out at the stars with wonder but unable to reach them. Perhaps the physics and engineering barriers we've discussed are genuinely insurmountable. Or perhaps the resources required are so enormous that no civilization finds it worthwhile. Better to build virtual worlds, mind-uploading paradises, or Dyson spheres around their home star than to launch futile expeditions into the void. There's also the time problem in a different sense. Even if we solved all the technical challenges and launched a generation ship tomorrow, technology continues advancing on Earth. A ship traveling at 10% of light speed takes 430 years to reach Alpha Centauri. But if propulsion technology improves, a faster ship launched 100 years later might overtake the first ship, arriving sooner. The original crew would arrive to find their descendants already there, having departed Earth centuries after them, but traveling on faster ships. This weight calculation suggests a perverse incentive. It's always better to wait for better technology. Unless you believe we've reached the pinnacle of propulsion physics, which seems unlikely given how many unsolved problems remain, any interstellar mission launched now will eventually be outpaced by future missions with superior technology. So why launch at all until we're certain our technology has matured? Yet waiting indefinitely means never going. At some point, if we're serious about reaching the stars, we must commit despite knowing future missions might surpass us. This requires a long-term civilizational perspective we've rarely demonstrated. Human institutions rarely plan beyond decades. Governments change, priorities shift, funding dries up. The only structures that have maintained purpose over centuries are certain religious institutions and cultural traditions. Could we create an institution committed to interstellar exploration that would sustain a mission for centuries, regardless of political changes, economic fluctuations, or public interest? The International Space Station offers a cautionary tale. This collaboration between 15 countries took decades to plan and build, launched in 1998, and has operated continuously since 2000. It's a triumph of international cooperation and engineering. Yet it's scheduled for decommissioning in 2030 or 2031, a mere 30-plus years of operation. The project cost roughly $150 billion. An interstellar mission would cost orders of magnitude more and need to function for centuries. What partnership could maintain commitment on such scales? Private space companies like SpaceX, Blue Origin, and others have renewed enthusiasm for space exploration. Elon Musk speaks openly about making humanity multiplanetary, with Mars as the first target. But even the most ambitious private ventures struggle with timescales beyond their founders' lifetimes. No private company has existed for centuries while maintaining a single focused purpose. Would SpaceX still exist in 200 years? Would its mission remain unchanged? History suggests corporations rarely survive beyond a few generations. Let's consider the physics one more time, but from a different angle. The speed of light isn't just an engineering limit, it's woven into the structure of space-time itself. Einstein's relativity shows that space and time are not separate, but aspects of a unified space-time fabric. The speed of light is the conversion factor between space and time dimensions in this fabric. Massive objects can't reach light speed because doing so would require infinite energy and would cause time to stop flowing for the object. But relativity offers a strange consolation. Due to time dilation, travelers at near light speed experience time more slowly. From their perspective, the journey is shorter. At 99.9% of light speed, time passes about 22 times slower for travelers. A journey that takes 100 years for Earth observers would feel like 4.5 years to the crew. Push closer to light speed, 99.99%, and the time dilation factor increases to 71. That 100-year journey now feels like just 1.4 years to travelers. In principle, if you could reach speeds infinitesimally close to light speed, you could cross vast distances while experiencing only modest time passage. You could travel to distant galaxies in what feels like a human lifetime, though millions of years would pass on Earth. But this brings us back to the energy problem. Reaching such speeds requires energies we can't produce. And there's a philosophical question. If millions of years pass on Earth during your journey, everyone and everything you knew is gone. You're traveling not just through space, but into the deep future. Is that really exploration, or is it abandoning your civilization? Breakthrough. Starshot's approach sidesteps some problems by accepting others. Gram-scale probes can be accelerated by external lasers without carrying fuel. At 20% of light speed, they'd reach Alpha Centauri in about 22 years, within Mission Control's lifetime. But they can't slow down. They'd zip through the system at enormous speed, taking brief observations before vanishing into the void. They can't land, can't explore in detail, can't return samples. They're reconnaissance, not colonization. Even this modest goal faces challenges. Keeping a laser focused on a centimeter-scale sail across light years requires adaptive optics far beyond current capability. The probes would be hit by interstellar dust, and at 20% of light speed, even tiny grains could destroy them. They'd need minimal shielding, but adding mass defeats the point. The probes must be ultra-lightweight to accelerate with available laser power. It's a delicate balance that might not be achievable. Another proposed concept is the world ship, or O'Neill cylinder, taken to the extreme. Instead of a ship, build an entire rotating habitat containing thousands or millions of people with complete ecosystems, industry, and culture. This becomes a mobile civilization, potentially traveling between stars over millennia. The mass would be staggering, perhaps billions of tons. Acceleration would be measured in fractions of a meter per second squared, taking decades or centuries to reach cruising speed. But once moving, it could theoretically sustain human life indefinitely. The challenges are proportional to the scale. Building such structures requires resources from multiple planets and asteroid belts. The energy to accelerate them would dwarf everything we've discussed. And fundamental questions remain: would a civilization enclosed in an artificial world for centuries maintain the will to travel? Might they decide their rotating habitat is home enough and simply stay in interstellar space, becoming a nomadic civilization? Would they even remember Earth after enough generations? There's also the question of whether we should focus on interstellar travel at all, or instead on building habitats within our solar system. O'Neill proposed massive rotating cylinders at stable points in Earth's orbit, L4 and L5 Lagrange points. These could house millions of people with Earth-like gravity from rotation, powered by solar energy. You'd have all the advantages of space resources without the impossible challenges of interstellar distances. The solar system contains vast resources. The asteroid belt holds trillions of dollars worth of metals and minerals. The moons of Jupiter and Saturn have water ice. Mercury has constant solar energy. We could theoretically build habitats for trillions of people using solar system resources, far exceeding Earth's carrying capacity. Why struggle to reach other stars when we have barely utilized our own stellar neighborhood? This perspective suggests our cosmic destiny might not be spreading across the galaxy, but rather flourishing within our solar system. Building a truly spacefaring civilization that populates the space between planets with rotating habitats, mines asteroids, terraforms Mars, and perhaps creates fusion-powered colonies in the outer system. From this viewpoint, the desire to reach other stars is premature. Let's master our own system first. But there's a counter to this: diversity and resilience. A civilization confined to one star system, no matter how distributed across planets and habitats, is vulnerable to stellar-scale disasters. Our sun will eventually become a red giant in about 5 billion years, rendering the inner solar system uninhabitable. Long before that, the sun's gradually increasing luminosity will make Earth too hot for life in perhaps 1 to 2 billion years. While these timescales are vast, a truly long-term perspective requires eventually leaving the solar system or facing extinction. More immediately, rare but possible events could threaten solar system civilization. A nearby supernova or gamma-ray burst could bathe the inner solar system in lethal radiation. A rogue planet passing through could gravitationally disrupt planetary orbits. A close encounter with another star could perturb the Oort cloud, sending millions of comets into the inner system. The odds of these events are low, but over millions or billions of years, they become significant. So there's a philosophical tension. Pragmatically, we can't leave the solar system with current or near-future technology. The barriers are fundamental, rooted in physics and biology as much as engineering. But long-term survival seems to require spreading beyond one star system. This suggests we're in a waiting period, centuries or millennia, during which we must solve problems we don't yet know how to solve. Fusion propulsion, antimatter production and storage, generation ship life support, radiation protection, and perhaps even life extension or hibernation to make human bodies compatible with interstellar timescales. In the meantime, robotic exploration makes sense. We can send increasingly sophisticated probes to explore the solar system and eventually nearby stars. Each mission teaches us more about operating in deep space, surviving radiation, navigating at extreme distances, and communicating across light years. By the time we're technologically ready for crewed interstellar flight, if that ever happens, we'll have centuries of robotic exploration experience to draw upon. It's worth considering alternative approaches to spreading life beyond Earth. Instead of transporting humans physically, what about sending genetic information? A probe could carry human DNA sequences and instructions for creating humans, along with artificial wombs and robotic caretakers. Upon arriving at a habitable world, the probe could begin producing human children, raised by AI, until they could form a colony. This avoids keeping humans alive during the journey while still establishing human presence on other worlds. This approach raises profound ethical questions. Is it ethical to create humans in an alien environment with no contact with human culture, raised by machines? Would they be psychologically healthy? Would they consider themselves human? Would they resent being brought into existence on a world they didn't choose? These questions don't have easy answers, but they illustrate the moral complexity of interstellar colonization. Digital consciousness offers another speculative route. If we could upload human minds into computers, a huge if, then people could travel as data, either on physical probes or potentially as radio transmissions moving at light speed. Upon arrival, they could be instantiated in robotic bodies or virtual environments. This sidesteps biological fragility, radiation damage, and food requirements, but it assumes we can digitize consciousness, which we're nowhere near achieving and might be fundamentally impossible. Even if possible, philosophical questions abound. Is an uploaded mind really you, or just a copy that thinks it's you? If the original biological you continues existing, who's the real you? If we transmit consciousness as radio signals, does consciousness survive being converted to electromagnetic waves and back? These aren't just academic questions. They go to the heart of identity and what it means to be human. Let's return to the cold equations. The energy required for interstellar travel, the mass of shielding and life support, the timescales involved, the radiation exposure, the navigation challenges, the communication difficulties, the psychological toll, the engineering complexity, the cost, and the fundamental physics barriers all point to the same conclusion. With current physics and any foreseeable extension of our technology, leaving the solar system is not just difficult, but bordering on impossible, at least for human beings in biological bodies. This doesn't mean we should stop trying to understand the universe beyond our solar system. Telescopes grow more powerful every decade. The James Webb Space Telescope peers deeper into space and time than ever before. Future observatories like the Extremely Large Telescope and potential space-based telescopes larger than JWST will reveal exoplanets in extraordinary detail. We can explore the universe through light, learning about distant worlds without physically visiting them. The search for extraterrestrial intelligence continues through projects like SETI, scanning the skies for artificial radio signals. If intelligent civilizations exist relatively nearby, within hundreds or thousands of light years, we might detect their transmissions. Communication would be slow, with messages taking years or centuries to cross the distance each way, but it would transform our understanding of our place in the universe. Learning that other intelligences exist, even if we can never visit them, would be profound. Some scientists propose active SETI, deliberately broadcasting messages to nearby star systems, announcing our presence. Others warn this might be dangerous, potentially attracting hostile attention. But if interstellar travel is as difficult as our analysis suggests, even hostile aliens couldn't easily reach us. The distances themselves provide protection. A civilization wanting to harm us would face all the same barriers we face trying to reach them. The speed of light protects as much as it confines. There's a melancholic beauty to this conclusion. We're confined to our solar system probably forever, or at least for centuries or millennia. We can observe the universe, learn about distant stars and galaxies, dream about alien worlds, but almost certainly never walk on them. We're like people in medieval villages who could see distant mountains but never had means to cross them. Except our mountains are light years away, and the journey would take not days but centuries or millennia. Yet confinement to the solar system doesn't mean limitation. Our solar system is vast, extending roughly 100,000 astronomical units to the Oort cloud's outer edge, and that's about 1.5 light years. Within this volume lies everything we need for a thriving spacefaring civilization: energy from the sun, metals and minerals in asteroids, water ice on moons and comets, space for billions of rotating habitats. If we can overcome our tendency towards short-term thinking, we could build a future where humanity numbers in the trillions, spread across millions of habitats orbiting throughout the solar system. We could have city-sized O'Neill cylinders at Earth's L5 point, mining operations in the asteroid belt, research stations on the moons of Saturn, solar collectors near Mercury. Each habitat could develop its own culture while remaining connected through communication networks that span the system. This vision is achievable with foreseeable technology. We don't need to break the laws of physics or invent impossible propulsion. We need strong materials, fusion power or efficient solar energy collection, closed-loop life support, and the political will to invest in multi-generational projects. These are enormous challenges, but they're not fundamentally impossible, like faster-than-light travel or generating infinite energy. Some argue that virtual reality will ultimately surpass physical reality. If we can create fully immersive virtual worlds indistinguishable from reality, why bother with the expense and danger of physical space exploration? Why travel to other planets when you can experience perfect simulations? This viewpoint suggests humanity's future might be increasingly virtual, with physical reality becoming less important. There's something unsettling about this vision. Humanity retreating into simulated realities, abandoning the physical universe. But perhaps it's pragmatic. The physical universe is vast, hostile, and bound by laws that make exploration difficult. Virtual universes can be anything we imagine, free from physics constraints. We could explore simulated alien worlds more easily than traveling to real ones. Yet part of being human is the desire for authentic experience. A simulated beach sunset, however perfect, isn't the same as a real one. A virtual Mars colony isn't the same as actually walking on Mars. Something in us rebels against the idea of permanent retreat into virtual reality. We're evolved to interact with physical reality. Abandoning it entirely might diminish something essential about human experience. The truth likely lies somewhere between pure virtuality and pure physicality. We might spend time in virtual environments for work, education, or entertainment while maintaining physical existence and continuing physical exploration at the pace the universe allows. Virtual reality could let us imagine and explore possibilities, while physical exploration proceeds at its slower, harder, more expensive pace. Looking at our cosmic confinement from another angle, perhaps it's not a limitation, but a blessing. The distance between stars means civilizations develop independently, creating diversity across the galaxy. If interstellar travel were easy, one aggressive civilization could potentially dominate the galaxy, destroying or assimilating all others. The difficulty of interstellar travel might be the universe's way of ensuring diversity and independence. From this perspective, our solar system is our garden to tend. We're responsible for making life flourish here, for developing a sustainable civilization, for preserving and spreading Earth's biosphere to other worlds in our system. We're not explorers destined to conquer the galaxy, but gardeners cultivating our small patch of cosmic soil. There's humility in this role, but also beauty and responsibility. Indigenous wisdom from various cultures speaks of being stewards rather than conquerors of the land. Perhaps that applies cosmically as well. We're stewards of the solar system, not conquerors of the galaxy. Our job is to understand, preserve, and flourish within our cosmic home, not to escape it. This reframing transforms apparent limitation into meaningful purpose. The Voyager 1 and 2 spacecraft, launched in 1977, are now in interstellar space, having crossed the heliopause, where the Sun's influence gives way to the interstellar medium. They're humanity's most distant ambassadors, carrying golden records with sounds and images of Earth, messages to any civilization that might someday find them. At their current speeds, they'll drift through the galaxy for billions of years, long after human civilization has either transcended into something unrecognizable or vanished entirely. These probes represent what we can achieve, sending tiny messengers into the void, carrying information about who we were and what we wondered about. They'll never reach another star system in any meaningful time frame. Voyager 1, if it were headed toward the nearest star, would take over 70,000 years to arrive. But they're out there, proof that we tried, that we reached beyond our limitations, even knowing we couldn't truly escape them. There's profound courage in that. The engineers who designed Voyager, the scientists who chose what to include on the golden records, the people who funded and built these missions, all knew the probes would outlast human civilization, would wander the galaxy long after we're gone. They built them anyway, sending forth our greeting to a cosmos that might never answer. That's the human spirit in action, doing difficult things not because they're practical, but because they matter. As we conclude this exploration of why we can't leave the solar system, remember that limits aren't failures. The speed of light limit exists because space-time has structure. The energy requirements are enormous because mass and energy are equivalent, as Einstein taught us. The distances are vast because the universe is vast. These aren't flaws in our technology or failures of human ingenuity. They're features of reality, the rules by which the cosmos operates. Understanding these limits doesn't diminish us. If anything, it enhances appreciation for how special Earth is. The only place in the universe we know with certainty can support human life. We evolved here over billions of years of evolution, shaped by Earth's gravity, atmosphere, climate, and ecosystems. Every cell in your body is adapted to this exact environment. We're not separate from Earth, looking out at the universe. We're Earth's way of looking at itself, products of this planet trying to understand our context. The atoms in your body were forged in stars that died before our sun formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar furnaces or supernova explosions. You're made of stardust, literally. You're the universe contemplating itself. The barriers to interstellar travel don't change that cosmic connection. Perhaps our destiny is not to physically spread across the galaxy, but to understand it deeply, to be the universe's consciousness, to observe and comprehend and appreciate the vast cosmic story of which we're a tiny but aware part. Through our telescopes, we can see the universe's birth in the cosmic microwave background. Through our experiments, we uncover fundamental laws. Through our mathematics, we describe reality's deep structure. We're confined to one star system, but our minds and instruments reach across the cosmos. The next time you look at the stars, remember they're not destinations we'll visit, but neighbors we'll observe from a distance. The distance that separates us from them is the same physics that allows stable atoms, chemistry, planets, and life. The speed of light limit that prevents us from reaching them is the same rule that prevents causality from breaking down and reality from becoming chaos. The barriers aren't bugs, they're features. We're trapped in the solar system, probably forever. But this solar system, this tiny corner of the galaxy, is our home. It's where life emerged from chemistry, where consciousness arose from complex nervous systems, where intelligence developed and began asking questions about existence. It's where music was created, where art captures beauty, where science reveals truth. It's where love happens, where wonder sparks, where meaning is found. The solar system is enough. It has to be enough because it's what we have. And perhaps that's okay. Perhaps the question isn't, how do we leave, but how do we thrive here? How do we build a civilization that lasts not just centuries, but millions of years? How do we spread life to every accessible corner of our stellar neighborhood? How do we ensure that consciousness and wonder continue as long as the sun shines? These are worthy questions, meaningful purposes. We can't reach the stars, but we can make our solar system a garden of life and thought. We can send our messages outward on voyages and radio waves, knowing we'll likely never receive replies, but sending them anyway, because it matters to try. We can keep looking up, keep wondering, keep learning, keep being amazed by a universe we'll mostly experience through light that travels across space to find us. If you made this far, you are exactly who I make these videos for. So make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we will never colonize Mars. In this video, we break down the hard scientific, engineering, economic, and biological realities that make Mars colonization nearly impossible for humanity. See you there.